What if I told you that right now, at this very moment, there's another version of you living in a universe where time flows backward, where every action you take here creates a mirror consequence there, and the Big Bang wasn't a beginning at all, but a meeting point between the two realities? This isn't science fiction. Well, not entirely. It's a radical new model of cosmology that's gaining serious traction among physicists, and it might fundamentally change how we understand reality itself. I'm talking about CPT symmetry and the holographic universe, two concepts that, when combined, suggest our cosmos is far stranger than we ever imagined. By the end of this video, you'll understand why some of the brightest minds in physics think we live in a universe with a mirror twin, why photons might be the only bridge between these worlds, and how Star Trek got closer to the truth than anyone realized. So buckle up. We're about to dive deep into the looking glass. Let's start with what we think we know. The standard model of cosmology tells us that about 13.8 billion years ago, everything in our universe emerged from an infinitely dense point in an event we call the Big Bang. Space and time began expanding. Matter cooled and condensed into stars and galaxies, and here we are. But here's the weird part. When we actually look at what the universe is made of, we find that only about 5% is normal matter, the stuff you and I are made of, the stuff stars are made of. About 20%, 27% is dark matter, which we can't see but know exists because of its gravitational effects. And a whopping 68 to 70% is dark energy, this mysterious force that's actually accelerating the universe's expansion. To explain some of the universe's properties, why it looks so uniform in all directions, why it's so flat, cosmologists introduced something called cosmic inflation. The idea is that in the first fraction of a second after the Big Bang, the universe expanded exponentially fast. Inflation theory predicts we should find long wavelength gravitational waves rippling through space-time from this violent early expansion. But there's a problem. Despite years of searching with increasingly sensitive instruments, we haven't found these primordial gravitational waves. Not definitively anyway, but that's where things get interesting. There's another mystery that's bugged physicists for decades. When we create matter in a lab, we always create antimatter in equal amounts. Antimatter is like matter's evil twin, identical in every way except with opposite charge. When they meet, they annihilate in a flash of pure energy. So if the Big Bang created equal amounts of matter and antimatter, where did all the antimatter go? Why is our universe made almost entirely of matter? Standard cosmology has some answers involving CP violation, tiny asymmetries in the laws of physics, but they're not entirely satisfying. Enter physicists like Neil Turok and his colleagues. They asked a radical question. What if we've been thinking about the Big Bang wrong this whole time? To understand their proposal, we need to talk about one of the most fundamental principles in physics, CPT symmetry. These letters stand for charge, parity, and time. Charge symmetry means that if you flip all particles to their antiparticles, the laws of physics stay the same. Parity means if you flip left to right, like looking in a mirror, physics still works. Time symmetry means If you reverse the direction of time, the fundamental equations don't change. Now, here's the crucial part. Individually, these symmetries can be broken. We see it all the time. But combined together, CPT as a whole, this symmetry appears to be sacred. Every experiment we've ever done suggests that CPT symmetry is conserved in nature. So Turok and his team, building on ideas from earlier physicists, asked, what if CPT symmetry isn't just conserved in our universe, but across the entire cosmos? What if the Big Bang is actually a Janus point named after the two-faced Roman god who looks both forward and backward, where two universes branch off in opposite directions? In this model, there's our universe where time flows forward, but there's also a mirror universe on the other side of the Big Bang where time flows backward, or more accurately, where entropy increases in the opposite temporal direction. To us, their time would look reversed. To them, our time would look reversed. Now, you might be thinking, well, wait, time flowing backward? That sounds insane. But here's the thing. Time isn't really a fundamental feature of the universe. What we call time is really just the direction of increasing entropy, the arrow from order to disorder, from low entropy to high entropy. The second law of thermodynamics says entropy always increases, and that's what gives time its direction. In the mirror universe, entropy would still increase, but in the opposite temporal direction from the Big Bang. From our perspective, their universe would look like it's running in reverse. But from their perspective, they're moving forward through time just like we are, and we're the ones going backward. Both universes would be obeying the second law of thermodynamics. Both would see entropy increasing from their perspective. The Janus point, the Big Bang, is simply the moment of lowest entropy for both universes combined. And here's where it really gets elegant. In this framework, our universe is made of matter and the mirror universe is made of antimatter. This solves the antimatter problem instantly. We don't need to explain where the antimatter went. It's over there in the other universe. Perfect symmetry, perfect balance. This isn't just speculation. Turok's work, along with collaborators Latham Boyle and Kieran Finn, has been published in peer-reviewed journals. Their landmark 2018 paper, CPT Symmetric Universe, published in Physical Review Letters, Volume 121, laid out the mathematical framework, and subsequent work has explored the testable predictions. One of the most striking predictions is that, unlike inflation theory, the CPT symmetric model predicts we should not find long wavelength gravitational waves from the very early universe. It also predicts that at least one of the three types of neutrinos in our universe must be exactly massless. Current measurements suggest neutrinos have extremely small but non-zero masses, though definitively proving one is exactly zero remains a challenge for future experiments. These are testable predictions. They're falsifiable. That's what makes this real science and not just philosophical speculation. Now, let's add another layer to this cosmic puzzle, the holographic principle. This is one of the most mind-bending ideas in modern physics, and it might explain what the Janus point actually is. The holographic principle emerged from studying black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered something strange. The entropy of a black hole, the amount of information it contains, is proportional to the surface area of its event horizon, not its volume. Bekenstein's 1973 paper, Black Holes and Entropy, in Physical Review D, established this foundational connection. Think about it. All the information about what's inside a black hole can be encoded on its two-dimensional surface. It's like how a hologram works. You encode 3D information on a 2D plate, and when you shine light through it, you'll get a three-dimensional image. Physicists like Leonard Susskind and Gerard 't Hooft took this further in the 1990s. Suskind's 1995 paper, The World as a Hologram, in the Journal of Mathematical Physics, posed the question, what if this isn't just true for black holes? What if our entire three-dimensional universe is actually a projection from a two-dimensional boundary? The mathematical framework that really made this rigorous is called the anti-de Sitter CFT correspondence. Developed by Juan Maldacena in his groundbreaking 1997 paper, The Large N Limit of Superconformal Field Theories and Supergravity in Advances in Theoretical and Mathematical Physics. It's the publication volume was called Advances in Theoretical and Mathematical Physics. It's a specific example proving that a 3D universe with gravity can be perfectly described by a 2D quantum theory without gravity. It's not just an analogy, it's a mathematical equivalence. This led to actual experimental tests. At Fermilab, physicists built something called the holometer, two high-precision laser interferometers designed to detect. This led to actual experimental tests. At Fermilab, physicists built something called the holometer, two high-precision laser interferometers designed to detect whether space-time itself has pixelated structure at its tiniest scales, which the holographic principle predicts. More recent work in 2026 has focused on quantum error correction. Physicist Ahmed Almhiri, Almheiri, Zedong, and Daniel Harlow published influential work in 2015 in the Journal of High Energy Physics, titled Bulk, Locality, and Quantum Error Correction in Anti-de Sitter Space, CFT, showing that space-time itself might be held together by quantum entanglement and that the structure of space emerges from information encoded on lower dimensional boundaries. Now, I need to be honest with you here. The holographic principle isn't proven. These are real challenges and evidence that complicates the picture. The most direct test came from Fermilab's holometer experiment, led by physicist Craig Hogan. Between 2009 and 2015, they used precision laser interferometers to look for holographic noise, the graininess in space-time that should exist if the universe is pixelated like a hologram. They found nothing, no evidence of the quantum jitter that the holographic principle predicts at small scales. Some of the very inventors of the holographic principle said that the experiment couldn't actually test it properly. The null result doesn't disprove holography, but it does show that if the universe is holographic, it's not in the simple pixelated way some researchers expected. There's a bigger problem, though. The anti-de Sitter space CFT correspondence, the mathematical proof that holography works, only applies to anti-de Sitter space, a universe with negative curvature that's contracting. Our universe is expanding with a positive curvature. It's de Sitter space. Anti-de Sitter space / CFT doesn't directly apply to our universe. Physicists like Maldacena are working on extending the holographic idea to universes like ours, but that work is still speculative. Physicists like Maldacena are working on extending the holographic idea to universes like ours, but that work is still speculative. That said, there is some observational support. A 2017 study by researchers at the University of Southampton. That said, there is some observational support. A 2017 study by researchers at the University of Southampton, University of Waterloo, and Italian institutions found patterns in the cosmic microwave background. That said, there is some observational support. A 2017 study by researchers at the University of Southampton, University of Waterloo, and Italian institutions found patterns in the cosmic microwave background that could be explained by holographic models just as well as by inflation theory. The evidence doesn't prove holography, but it shows it's competitive with traditional explanations. Now, here's where this connects to the CPT symmetric universe model. What if the Janus point, the Big Bang, is actually a two-dimensional holographic screen? A boundary of pure information where the source code for both universes is written. In this framework, the Big Bang isn't a point in space, it's an interface, and the only particles that can exist at this interface are photons and gravitational waves. Particles that are their own antiparticles, particles that can exist in both the matter universe and the antimatter universe without being destroyed. Think of the Big Bang as a radiation-dominated era where everything was photons, high-energy light. As the two universes separated from this photon-rich boundary, moving in opposite temporal directions, that light cooled and condensed into matter in one universe and antimatter in the other. We still see the remnants of this primordial light today. It's the cosmic microwave background radiation, the afterglow of the Big Bang. In the holographic framework, this is literally the light from the 2D interface being projected into our 3D space. Some physicists have even suggested that dark energy, that mysterious 70% of the universe pushing space apart, might be the pressure from this photon-heavy interface, the energy of the Big Bang mirror still pushing the two universes away from each other. Okay, let's take a brief detour into science fiction, because sometimes the storytellers get there before these scientists. I want to talk about a couple of Star Trek episodes that, whether intentionally or not, touch on these very concepts. The first is a 1967 episode called The Alternative Factor. In this episode, the Enterprise encounters a man named Lazarus who's hunting his twin from an antimatter universe. There are two Lazaruses, one from a matter universe and one from an antimatter universe, and they exist in two different dimensions, separated by a magnetic corridor. The episode's central threat is that if these two identical beings meet in either universe, both universes will be destroyed. They'll wink out of existence. The solution is to trap both Lazaruses in the corridor between universes, fighting for eternity. Now, this is 1967, remember. The CPT symmetric universe model didn't exist yet. But look at how well this maps onto what we've been discussing. The two Lazaruses represent the matter and antimatter universes. The corridor between them is the holographic screen at the Janus point, the 2D boundary where the source code for both universes exists. The threat of universal annihilation if they meet reflects what happens when matter and antimatter collide. The ending, with both Lazaruses trapped forever in the corridor, actually suggests something profound about the block universe interpretation of time. They've become a fixed point in the four-dimensional geometry of space-time, locked at the mirror point where time has no direction. The other episode I want to mention is All Good Things, the finale of Star Trek The Next Generation. In this episode, Captain Picard experiences time non-linearly, shifting between past, present, and future. Q tells him that humanity is being tested on its understanding of time and existence itself. The plot involves an anti-time anomaly that's growing backward through time, threatening to prevent humanity from ever existing. 3 versions of Picard from different time periods must work together to collapse the anomaly. What's fascinating here is the concept of anti-time, time running in the opposite direction. The anomaly grows larger the further back you go, eventually reaching the moment when life first appeared on Earth. This is strikingly similar to the idea of retrocausality in the mirror universe model. In the CPT framework, inhabitants of each universe would observe what looks like retrocausality in the other universe. Effects would appear to precede causes from our perspective because time is flowing in the opposite direction there. The episode also touches on the Novikov self-consistency principle, which is increasingly favored by physicists in 2026. This principle states that if time travel to the past is possible, the timeline must be self-consistent. You can't change the past because your actions were always a part of what created it. In the holographic framework, this makes perfect sense. If our 3D universe is a projection from a 2D source code, you can't change the past because it's already encoded in the hologram. The geometry is fixed. Every apparent time travel scenario would resolve in a way that maintains consistency with the 2D information. Let's talk about The Terminator, the movie. Because this franchise has tortured time travel enthusiasts for decades with its apparent paradoxes. In the original 1984 movie, a cyborg assassin is sent back from 2029 to 1984 to kill Sarah Connor before she gives birth to John Connor, the future leader of the human resistance. Kyle Reese is sent back to protect her. He becomes John's father. The photo of Sarah that John gives Kyle in the future was taken during the events of 1984. The technology that Skynet is built on comes from the destroyed Terminator's remains. It's a closed loop. Traditional physics hates this. It's called bootstrap paradox or causal loop. Where did the information come from? Who created Skynet first? Who fathered John Connor originally? It seems to violate causality. But in the block universe interpretation, combined with the holographic principle, these aren't paradoxes at all. Time isn't a river that flows, it's a dimension like space. The entire timeline, past, present, and future, already exists as a 4-dimensional structure. If our 3D universe plus time is a projection from a 2D holographic screen, then the entire history is encoded on that screen. The causal loop isn't a problem, it's a feature. It's part of the consistent geometry of the 4D space-time that was always encoded in the 2D source code. This is where the Novikov self-consistency principle comes in. If you went back in time to 1984, you wouldn't create a new timeline. You would find that every action you take, including your attempts to change things, were already part of the original timeline. You can't save Sarah Connor from the Terminator if she's supposed to survive, and you can't kill her if she's supposed to survive because the universe's geometry is consistent. From a physics standpoint, this involves closed time-like curves, paths through space-time that loop back on themselves. General relativity allows these under certain exotic conditions like rotating black holes or traversable wormholes. But in the holographic framework, time travel isn't about physically moving through time. You'd be accessing different slices of the 2D holographic code and manifesting there. The 3D projection you experience in 1984 is just a different cross-section of the same 4D geometry that was always there. So the Terminator's timeline isn't a paradox. It's a self-consistent loop encoded in the geometry of space-time itself. John Connor gives Kyle Reese the photo and sends him back because that's what the 2D source code says happens. Kyle fathers John because that's what's encoded. Kyle fathers John because that's what's encoded. Skynet gets built from the Terminator's remains because that's what's part of the consistent structure. The sequels muddy this by suggesting you can change the future, but the original film's closed loop is actually more consistent with modern physics. There's no original timeline. There's only the one timeline that exists as a complete, self-consistent, four-dimensional object. Now, let's talk about something that sounds like pure science fiction, but might actually be possible in this framework: warp drives. How would faster-than-light travel work if we live in a holographic universe with a CPT symmetric mirror twin? In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's field equations that would allow faster-than-light travel without violating relativity. His paper, The Warp Drive: Hyperfast Travel Within General Relativity in Classical and Quantum Gravity, showed that the Alcubierre drive works by contracting space-time in front of a ship and expanding it behind, creating a warp bubble that surfs through space while the ship itself remains stationary relative to its own local space-time. The problem has always been energy. Alcubierre's original calculations required negative energy, exotic matter with negative mass, and absurd amounts of it. We're talking about converting the mass energy of Jupiter just to move a small spacecraft. Not exactly practical, but here's where things get interesting. In 2012, Harold White discovered that by changing the geometry of the warp bubble, making the ring thicker, more like a torus or donut shape rather than a thin wedding band, and oscillating its intensity over time, the energy requirements drop dramatically, from Jupiter mass down to something closer to the Voyager 1 spacecraft, about 700 kilograms. Still exotic matter we don't know how to create, but orders of magnitude more feasible. Even more recently, in late 2025, White proposed breaking the continuous ring into discrete cylindrical structures he calls warp nacelles. Yes, like Star Trek's Enterprise. These would distribute the exotic energy requirements into separate engine-like pods, keeping the interior of the bubble stable and habitable. But here's where the holographic universe model changes things. If our 3D space is a projection from a 2D boundary, then space-time isn't fundamental, it's emergent. It's information being processed and projected. Think of it like a video game. In a game, you don't actually move through physical space. The computer updates pixels on a screen based on underlying code. If you wanted to teleport in the game, you wouldn't need to physically move matter, you'd just change the coordinates in the code. In the holographic framework, a warp drive wouldn't be about manipulating 3D space-time directly. It would be about manipulating the 2D holographic code that generates that space-time. You'd be editing the source code rather than brute forcing the projection. Recent work in quantum gravity, particularly the ER equals EPR conjecture by Juan Maldacena and Leonard Susskind in their 2013 paper Cool Horizons for Entangled Black Holes, published in, this is German, Fortschritt der Physik, suggests that quantum entanglement and wormholes might be the same thing. Entangled particles are connected by tiny wormholes through the holographic boundary. If you could create and control quantum entanglement at a macroscopic scale, you might be able to create shortcuts through the holographic boundary. essentially rewriting which part of the 3D projection you're manifesting in without traversing the space in between. Here's where it gets really interesting. Remember, photons can exist at the holographic boundary, the interface between universes. They are their own antiparticles. They can bridge the matter and antimatter universes. What if the speed of light isn't a fundamental speed limit of the universe, but rather the refresh rate of the holographic projection, the maximum speed at which information can propagate from the 2D boundary into the 3D space? In this model, a warp drive might work by creating a localized region where you're accessing the holographic boundary directly, essentially creating a window in the 3D projection where you can interact with the 2D code. You'd manipulate the information flow from the boundary, changing your position in the projection without moving through the projected space. The energy requirements might be dramatically different too. Instead of needing Jupiter's mass in exotic matter, you might only need enough energy to create a controlled interface with the holographic boundary, potentially achievable with intense coherent photon fields or carefully engineered quantum entanglement. Here's a wild implication. If gravity interacts with both universes and photons can exist at the boundary between them, a warp drive might inadvertently create effects in the mirror universe. Your warp field in our matter universe might generate a corresponding distortion in the antimatter universe. From our perspective, we're moving forward through space, but from the mirror universe's perspective, with time flowing backward, your warp trajectory might appear as retrocausal, an effect preceding its cause. Your destination might seem to know you're coming before you leave. This isn't just speculation. Physicists like Harold Sonny White at NASA's Advanced Propulsion Lab have been seriously studying warp drive mechanics. White's 2013 paper, Warp Field Mechanics 101, from NASA Johnson Space Center, explored practical approaches to creating warp fields. And while their work predates the holographic CPT model, combining these frameworks might offer new approaches. Current research into quantum error correction in spacetime, the idea that space itself is held together by quantum information, might provide the theoretical foundation for actually building something like this. If we can understand how to read and write to the holographic code, we could potentially manipulate spacetime in ways that seem impossible from a classical physics perspective. Now, let's shift gears and talk about one more fascinating aspect of the CPT symmetric universe model: right-handed neutrinos and their connection to dark matter. In our universe, we observe what are called left-handed neutrinos. This refers to their chirality, the direction of their spin relative to their motion. These neutrinos interact through the weak nuclear force, but they're incredibly light and fast-moving. Physicists call them hot dark matter because of their high velocities. But dark matter, the 27% of the universe we can't see, needs to be cold, meaning slow moving, to explain galaxy formation and structure. Hot dark matter moves too fast to clump together the way we observe dark matter behaving. Here's where the CPT symmetric model gets interesting. If charge, parity, and time, CPT, are all flipped in the mirror universe, then the particles there would have the opposite chirality. Their neutrinos would be right-handed from our perspective, and right-handed neutrinos, if they exist, would be much more massive and slower moving than left-handed ones. They'd be cold dark matter candidates. Some physicists have suggested these sterile neutrinos could account for the dark matter we observe. In the CPT framework, dark matter might not be some exotic particle in our universe at all. It might be the gravitational influence of the mirror universe bleeding through. Remember, gravity interacts with both universes It's not limited by the matter-antimatter divide. The clumping of dark matter we observe could literally be the gravitational footprint of antimatter structures in the mirror universe. We can't see them directly, but we feel their gravity because gravity transcends the holographic boundary. This is highly speculative, of course. We haven't detected right-handed neutrinos yet, but the prediction that they should exist and that at least one neutrino type should be exactly massless gives us something concrete to test. So where does this leave us? We've journeyed from the standard Big Bang model through CPT symmetry, the Janus point, the holographic universe, explored warp drives as information manipulation, and even detoured through Star Trek and the Terminator. What does it all mean? The truth is, we don't know yet. The CPT symmetric mirror universe model is one hypothesis among several competing frameworks. It makes testable predictions, which is exactly what we need. Over the next decade, observations of gravitational waves, neutrino masses, and the structure of space-time at quantum scales will help us determine if this model reflects reality or if we need to keep searching. What's certain is that our universe is far stranger and more elegant than we imagined even a few decades ago. The idea that time might not be fundamental, that we might live in a holographic projection, that there might be a mirror universe made of antimatter where time flows backward, these aren't idle fantasies. They're serious scientific proposals backed by mathematics and making predictions we can test. If the model is correct, then photons, light itself, might be the only bridge between our universe and its mirror twin. The cosmic microwave background radiation we see isn't just the afterglow of the Big Bang, it's literally the interface, the 2D holographic screen where both universes meet. Standing at the edge of our universe, you wouldn't see a wall. You'd see a horizon of pure light, the same light that created the matter on our side and the antimatter on the other. Everything we are, everything we observe, might be a projection from that boundary of information. The implications are staggering. If space-time is emergent from a holographic boundary, then technologies like warp drives aren't about brute force physics. They're about understanding the underlying code of reality. We might be closer to practical, faster-than-light travel than we think, not because we'll overcome the light barrier, but because we'll learn to rewrite the rules at a more fundamental level. The next time you look up at the night sky, remember, you might be looking at the ghosts of another universe, reflected through the photon interface that connects all of reality. And somewhere in a mirror cosmos on the other side of time, another version of you might be looking back, and the stars between you might not be as unreachably far as they seem. Thanks for watching. If you enjoyed this dive into the deep end of cosmology, consider subscribing. There's a lot more strange physics where this came from.